Okay, so let's start this second session of the conference. So, okay, the first speaker is Daisuke Ishii, and he will talk about a real blasting extension of Cvc5 for reasoning about floating point arithmetic. So,
Okay, thank you for the introduction. So, my name is Daisuke Ishii, and this maybe I should stand here. So, this is a presentation of a tool paper about an extension of Cvc5 SMT solver for reasoning about floating point arithmetic. So first of all, let me give you a brief overview of floating point arithmetic. FPA, in short, enables reasoning about numerical systems by SMT solvers. So here we have a simple formula in FPA, which involves variable x of the sort of 8-bit FP numbers. And so SMT-lib also provides the floating point theory so that you can describe like this as well. And when solving this kind of problem with SMT solvers, the standard technique, a standard approach is bit bursting. So with this bit bursting approach, we prepare bit vectors for the variables and the constants in the formula, and also encodes a circuit for the basic FPA operations. And roughly speaking, the problem is translated into an instance of the propositional subprogram. Okay, so at present, an issue with the bit bursting approach is scalability. So, for instance, if we modify the sort of variable x here into the sort of 64-bit FP numbers, then obviously the number of encoded bits will increase accordingly, so that results in a large SAT instance. And on the other hand, SMT solvers are good at handling real arithmetic formulas. So, for example, if we can somehow have an approximated formula for the original formula, like this one, then sometimes we can solve the formula very quickly. So based on the observation like this, here comes the idea of this real bursting approach. So this real bursting approach, it means to solve FPA problems in real integer arithmetic, assuming axiomatization of FPA. Actually, the name real bursting is put by me, following bit bursting and int bursting, which was proposed recently. But the idea is not new. There exists studies on the same approach. But anyway, with this approach, we prepare an axiomatization of FPA in an extended real arithmetic, like this one. So, so this example is on the multiplication operator. So, for example, an axiom here describes the finite case of the operation. So, with some conditioning here, it is saying that the value of the operator should be the rounded value of the mathematical product. And the axiom here is for the case of having -0, and so on. So this real blasting approach solves FPA problems in RRA, assuming the axiomatization like this. But the key point here is lazy manner of instantiating the axioms. So in practice, it is efficient to have firstly having an abstracted formula like this one, where the multiplication term is represented by a fresh variable. And here and here, we have placeholders for putting some additional constraints. So, for example, here, this placeholder is representing the subset of axiom instances that characterizes the value for the variable here. So there exists tools implementing the approach, but according to the preliminary experiments, the performance is quite limited, maybe due to the prototype status of the tools. So the main question of this research is how far can we go by optimizing the implementation for the real blasting approach? So here are contributions of this research. First, we propose a new axiomatization of FPA. And then I have built a practical implementation within Cvc5 SMT solver. So it was implemented as an alternative FPS theory solver. So Cvc5 has a default bit blasting solver. So my extension can be used as a kind of an option to it. And then using the tool, I have made experiments to evaluate the performance. And I somehow confirmed that our solver outperformed the bit blasting solvers for some practical bounded model checking instances. So I will come back to this in the later part. So let me explain some details. Okay, so first about floating point numbers. So they are numerals represented by epsilon number of exponent bits and sigma significant bits. But I just skipped the details. But here I assume floating point numbers following the standard. So we could consider a set of 8-bit FP numbers and set of doubles of each other, where epsilon is 11 and sigma is 53. Okay, so the elements of the set like this can be classified into several sorts. So first, we have the normal and subnormal numbers that can be mapped onto the real number line like this. So normal numbers can be placed on the blue region, and subnormal numbers can be placed around zeros. So by the way, we have 2 zeros. Some rationals are represented as FP numbers, so that, but other real numbers should have rounding errors. And so this plot shows how the errors distribute due to the design of this number system. And additionally, we have special values, namely positive infinity and negative infinity, and the not a number symbol. So what I propose in this research is a mapping like this from FP numbers to rationals. So what I did is easy, kind of easy. I just put special numbers outside the bound of normal numbers. And since we have two zeros, positive zero is mapped to real zero. And minus zero is just put next to the positive zero. But what's to be careful is that the special values are set properly so that they cannot be obtained by any FP operations. Then, based on this mapping, we can interpret FPA operators in RIA. So for instance, rounding operator can be interpreted like this as a function of this sort, and multiplication can be interpreted like this. And then on this interpreted function, we can describe a set of axioms. So for the rounding operator, for example, we can describe an axiom characterizing the idempotency of the operator and the relative round error bounds can be characterized like this, and so on. And for the multiplication operator, so this was shown in the beginning. So the finite case and the minus zero case can be described like this. So let me briefly explain the process with the tool. So first, as an example, we can let me consider this example. Then first, the tool translates the FPA formula into RIA. And in the beginning, in this case, is finite is expanded with its definition. And for FPA operators, usually they are initially translated into a purification variable. And this one is also somehow translated into a rational literal, like this. And then here we have two placeholders. And here we have a constraint for the variable, unbounded variable here, x, for having only the FP number assignments. And here we have, we put axiom instances for the multiplication term here. So, but we aim to detail this part gradually to be efficient. Okay, so this is a basic process, following basic process. So first, basically, we let the SMT solver to enumerate models for this interpreted formula. And then we check the consistency with the original formula. So for example, if we have a model like this, which represents an assignment like this, then we check whether it is okay by evaluating the concrete term, each of the concrete terms. So for instance, the condition for the variable x is okay, and we evaluate we simplify the multiplication term so that we can check that it is equivalent to the constant. And in the same way, likewise, we can check for the given inconsistent model, we can also check it in the same way. So this process is done by this rewrite function of the tool. And in the middle of the solving process, two approaches for the axiom instantiation is used. So we have this eager run method and the lazy run method. And the eager run is basically instantiate in the initial phase. So for each of the FPA term, a general definition like this is instantiated in the solving context. And for lazy run tries to instantiate an axiom in a lazy manner. So a typical well-known method to doing this is in SMT solvers is this e-matching with triggers mechanism used for the universally quantified constraints. But here we use a different method, which is called model-based refinement. So let me just show you an example. So for the example of this multiplication term, so assume initially we try to solve with no axioms instantiated. So we may have an inconsistent model, some inconsistent model. Then we try, this lazy run tries to refine the model based on this model-based refinement mechanism. So here, it somehow instantiates this axiom in this form. And this is done because the initial, current model here does not satisfy this instantiated axiom. So with this mechanism, we can efficiently instantiate during the solving process. Okay, so this process is implemented as an extension to Cvc5. Okay, so our implementation is based on the Cvc5 theory solver extension mechanism, so which supports this model-based refinement mechanism. So what I have explained so far, these three subroutines are easily implemented using this architecture of Cvc5. Okay, so in the rest of the talk, I would like to report some experimental results. So to answer these questions. So first one is about the correctness of the method and the implementation. And second and third are about the performance of the tool. So in the experiment, we have prepared 3 sets of benchmark instances. So first one is modified Winter-Steiger benchmark. So the Winter-Steiger benchmark is a major benchmark used for a kind of regression testing in this domain. So it contains many basic test cases like this one. So I have somehow modified each of them to make them abstract because in the aim of stressing our solvers. And the second benchmark is the Grischow benchmark, which is also a major benchmark in this domain to stress bit parsing solvers. And third one is prepared by me, which is an encoding of encoded formulas for the bounded model checking of simple reactive systems. Okay, and for the encoding, I have used these three, either of these three precisions. Okay, so in the experiment, experiment was done with these 5 solvers. So I have somehow prepared 2 solvers with our solver with different tunings, and other 3 are state-of-the-art FPA solvers. I mean, bit bursting solvers. And this is a result for the 2 benchmarks. So for the first one, it resulted that our solvers had around 15% of unknowns and timeouts. I will explain why later. And for the greater benchmark, so the state-of-the-art solvers are quite performed well. But for our solvers, we found that when solvable, our solvers was first. And this is for the bounded model checking experiment. So here and here, we could have best results among the solvers for some systems. And so maybe here, so this was expected, but we had the better scalability regarding the precision. Okay, so let me describe some discussions. So for the first question, we had no unsound results, so we consider the method and the implementation is correct. And for the second question, is our solver more efficient and scalable than existing solvers? So the answer is yes and no. So for some instances, we consider involving large numbers of arithmetic operators and also involving high precision FP numbers. Then our solvers performed well. And also, when the time limit is short, maybe our solvers can be better. And also, so this is kind of about the preliminary experiment. We also compared with existing real bursting solvers, and we confirmed that our solvers improved the performance a lot. And but for many instances, bit bursting solvers are still better. So maybe our solvers resulted in a number of axiom instantiations, so that the solving context becomes large, and it was inefficient. And also, for the first experiment with Winter-Steiger benchmark, we found that, according to my investigation, we had some corner case situations where, so I consider currently we are lacking some corner case axioms, so that we could not solve successfully. And for the third question, we could compare lazy run method and eager run method. And according to the experimental result, lazy run was more efficient for many instances, but there are also cases where eager run was better. Okay, so let me conclude. So I have presented an approach to regard FPA formulas as RIA formulas, and we have implemented the real bursting approach by using the extension mechanism of Cvc5. And in the experiment, we confirmed the better performance than existing solvers on some practical BMC instances. Okay, I think that's all. Thank you for listening.
You said that your approach is better sometimes, but not always. But have you characterized in some way in which cases your approach is more efficient or scalable, and while in which conditions you lose scalability and or efficiency?
So basically, currently our solvers easily resulted in a situation like this one I described here, where a lot of axiom instances are generated so that the context becomes too large, so that it's just kind of stuck in that situation. But if it is successful, it seems to be efficient. So, yeah, but the classification of the two cases, I have not yet done. So, yeah, I could not describe a clear observation here.
Is there any other question?
So, as I see it, you are taking a formula in linear real arithmetic and translating it to real integer arithmetic. Is that?
No, we are using nonlinear arithmetic solvers.
Okay. So if your formula is actually a linear real arithmetic formula, would it still remain linear after you do this, or is there a way to keep it inside the linear real arithmetic fragment by real blasting, or?
No, I haven't tried that.
Okay.
I think even if the original formula seems to be linear, we should have we can have some nonlinear terms.
So the reason I'm asking is in linear real arithmetic is very useful and very fast generally if you don't have the floating point, right? But then if you do multiplication of like known floating point numbers, right? So when you do linear real arithmetic, typically one of the floating point multiplication, one of the numbers will be known, right? So I'm just wondering if something special can be done if I know I'm multiplying it by 5 or 2.7 or 3.2, right? If one of the multiplicand is known, whether the translation can be improved. Maybe that's my question.
Yeah, I think that can be possible in some way. So actually, nonlinear solvers in Cvc5 itself is also an extended solver. So basically, it's at the bottom there is a linear solver. So yeah, maybe if we, yeah, so I mean, on the side of nonlinear solver of Cvc5, we can do something to be efficient, I think.
Okay, so let's thank the speaker again.
Thank you.